Hi, I was just wondering, with looking at the underwater volcanoes, and whether you have to, like, what assumptions you have to make that they act in the same way as surface volcanoes, or whether you need to make changes to what you know about the Earth ones. That
You sound like reviewer two. That's a kind of in-joke for academics. The amazing thing is there are so few seismic images of submarine volcanoes that have been studied in detail. It's actually hard to have an idea of what a large enough statistical data set of whether they are the same in terms of their size and their shape and things. What we know from modern seafloor images, we can see the outside of the volcano, but we have no idea about what's inside them. So we are really in the infancy of trying to relate submarine volcanism to subaerial volcanism. It's clear that some of the submarine volcanism will be more explosive because of the contact effects between the lava and the seawater. But how that then drives the volcano morphology, because those submarine volcanoes in the South China Sea look like regular subaerial volcanoes to me. So we are kind of just tiptoeing through some of the early stages of that work, really. The composition should be the same, the basaltic or doleritic and different things, yeah.
A question at the front here.
You had lots of examples from New Zealand and Australia. Is that a hotspot for fossilized
It's a good question.
volcanoes, or is that just pure luck or chance? Is that where most of... Was that like Japan millions of years ago?
You've looked into my soul, haven't you? So the reason we look at a lot of volcanoes from New Zealand and Australia, there's one really good reason, is because there's data there. So the Australian and New Zealand governments, unlike a lot of other governments, are very, very good at giving their data to academics to work on. Therefore, we go there. So geologically, Australia and New Zealand are very similar to lots of other places in the world, but we just don't have data from there. So that's one of the main reasons we are kind of using those sorts of data from those locations, is because we can get our hands on them. Okay. Yeah.
Great. Shall we take a question from the front row, please? Thank you, Lisa.
Hi, thanks. I was wondering, since it sounds like so much data, but can you use it, because you have the data, but can you use it to predict what can happen in the future and how it can change over time? So
Not publicly,
20 years or 50 years, what would be different if you look at the past and present?
Yeah, so the people who work in hazards don't want to talk about prediction. That term is very different from forecasting. So forecasting is to kind of give a likelihood or a probability of something of a certain size happening within a certain time window. Like forecasting or prediction is when you say next Tuesday at 5 o'clock this volcano will erupt. You know what I mean? So there's a slight difference there, and anybody who works with the Earth or any sciences really, not all sciences, but quite a few sciences, there's an unpredictability about the physics of what's going on in the Earth that we can't see, and it's really hard to measure, and it's hard to understand the dynamics. So I would never want to claim that this type of work and the improved understanding from these sorts of data will cure a problem we have. My personal feeling is that I think what we're doing with the reflection seismic data that I showed you today, we need to talk to the people working with active monitoring of volcanoes, and it's them who are more directly warning populations and talking to governments about, because you can't mitigate. The problem with volcanoes is you can't tell them not to erupt. You can't put a cork in it, right? So you can't stop it. And in fact, if you knew it was next Tuesday at 5 o'clock, that might be helpful to then leave at 4:50. But if you kind of say, well, there's a likelihood of an eruption in the next 10 years, if you lived there, where do you live?
Axon?
Do you live in
Somewhere
Acton?
where there's...
But if you live, if somebody said to you, in 30 years' time there's going to be a volcanic eruption, or there's a likelihood of a volcanic eruption, it's slightly higher in 30 years' time than 20 years' time, would you leave your home?
Probably not.
No,
Just
and
yet.
that goes back to a lot of the issues you have with hazard assessment and communication of risk to people, isn't it? Because people don't live around Etna, Vesuvius, Nyiragongo, St. Helens because they want to live next to a volcano. They live there because there are resources for the large part, right? People, if you're traveling around, there's resources, there's minerals, there's there's soil, lush vegetation. You end up living there and you'll take the risk, won't you? Like, well, next Tuesday it might not happen, so I'm going to stick around because if I leave, somebody's going to rob my house and take my cattle.
But can you make these mites? Because there's so many mites, but can you make things into certainties yet? So is there any way to be as accurate as possible, really?
There's a load of statistical work that goes around recurrence rates, same for earthquakes as well, magnitudes and the recurrence intervals. But it's not that great. To be honest with you, I want to be positive.
Great.
Can your fascinating technique throw any light on what's going on in the supervolcanoes such as under the Yellowstone?
Ooh. If you're a funding agency, yes.
Sadly, no.
Yeah, we'll talk afterwards. No, So seismic reflection imagery has been used in things like Yellowstone, Campo Flegrei, near Naples. The issues with, I'm not a geophysicist, but the issues with deployments of active source, we call it active source seismic experiments, so where you have to have an energy source. The problem is wandering around in many places of the world with dynamite or some big disturbance is really problematic. So it's very hard to environmentally collate those data, but also there's a series of kind of rather nerdy technical issues with how you, on land, you deploy the cables. So remember the marine survey I showed you, these things called hydrophones, they just trail freely behind the boat. If you're on land, you need to lay out those cables in a semi-permanent installation, and then you have to move the energy source, so you have something called offsets. So you end up having to lay these cables out, and there's a huge amount of logistical problems. To think about, Horse Hill Well in Gatwick, there was a well drilled there. Poole Harbour with Witch Farm oil field. There's a load of environmental and logistical challenges with getting the equipment so that you can get the energy down into the earth, for one, but then also have an array of things to record the energy that comes back from the rock. So it's really difficult, and the images, therefore, are not great. Yeah.
Okay. Hank, you've...
Yeah, very interesting, and I love the scientific progress. Hypothesis doesn't work. Another one, and what have you? If I can, two quick ones to get in. Are hotspots now basically been modelled? Is there any mystery to them? What have you? That's one. And the second one is the Deccan traps and continent-wide volcanicity. What are is there a consensus now on what would cause that to happen, or lots of different ideas, or what?
I mean, I'm not really a kind of, not really a volcanologist in that sense. I mean, what my understanding is that hotspots are still very much debated. I mean, there's good seismic tomographic evidence, like the picture I showed you from Mount St. Helens, where you can look at wave speeds, the fast or slow areas, and there looks like there's columns of rising molten material, so what you would call a hotspot. And so the Hawaiian hotspot is probably the most famous one. But there's some debate about how they've changed through time and how important they are. That relates to the Deccan traps. Why was there such voluminous and protracted, so lots of stuff, over a really long time, protracted. Why that happened, is it because you had a sustained source of melting, right? So one thing, to generate lots of magma, you need to melt material, and you need to do that for a long time. you can do that by lowering the melting temperature by adding water, is one way. So if you have water in the mantle, you could generate large amounts of melt. Or you can somehow perturb what we call the geotherm. So you can make it locally hotter there. And one way we can do that is by rifting, by pulling the Earth's crust apart. You raise the asthenosphere, and the crust gets hotter. So yeah, there's still discussions around that. I mean, these sorts of techniques are not particularly built for looking at those big, what we call lips, large igneous provinces. Although we did write a paper last year saying they could help. Now I think about it. Yeah.
Great. Should we take a question from the front row here? Hold on, I'm going to just...
When were you first kind of inspired to do geology?
Honestly, when I found out I was not very good at lots of other things. I honestly, so I went to school, I liked all my subjects, I did quite well at school in all the subjects, I loved sports. And then it was simply a case of maths, it's a bit hard. And then physics, it's a bit hard. And then I went to an A-level open day at it's called a tertiary college, a city college I went to, because my sixth form burnt down the year before I started there. That was nothing to do with me. Yeah, so I went to a tertiary college, and I went to this desk, and there was a guy there, I still remember his name, Robin Sedgwick. He was my A-level geology teacher. He was a biologist, but he had a passion for geology, so he offered GCSE and A-level geology. And he had this table, and it had little rubber dinosaurs and volcanoes, and I was like, that looks a lot better than physics table over there. And I think they had a Van de Graaff generator or something going, or somebody's hair was sticking up. And I just thought that didn't look as interesting as dinosaurs and volcanoes. So honestly, very small interactions like that, if you are interested in science, meeting the right person who inspires you. And I didn't know if I wanted to work on dinosaurs or volcanoes, and as it is, I've worked a bit on the latter, but it's just those moments are really important when you see something you think is really good fun. And honestly, the reason I kind of make that joke about being rubbish at lots of other things is you will want to do something, and you're more likely to do it well if you enjoy it, which sounds like a bit of an easy way, and it is a slightly privileged thing to say, but it doesn't need to be in academia. It can be in any walk of life. If you find something where you feel that you're valued and you can make a contribution, go and do it. It doesn't matter how much you get paid, but you'll do it well, and you'll come home happy at the end of the day.
How's it like being a geologist?
It's pretty rock and roll, I tell you. It's being a geologist. It is what's funny about being a geologist, and this is an honest answer. If your job is to look at what happened in the past, there's a kind of unhappiness and a sadness about never knowing the answer. Because we're using rocks, we're using these techniques, we're thinking, what did the volcano do 42 million years ago? And you know what I mean? It's not often the geology I do is not particularly experimental. It's kind of trying to build the Earth and reconstruct the Earth, what it looked like a long time ago. So there's a kind of real excitement about that, but then there's also a slight disappointment that you never know if you're right. Whereas if you're kind of doing things in a forward sense sometimes with experiments, it's slightly different. At least the stuff I do, that's not true for all earth scientists.
Great. Have another question, please. The lady with the child in her arms.
Hi, thank you very much for the exposé. Just wanted to ask you if you will live next to a volcano yourself. Because you love them. So will you live next to one?
Yeah.
So why you think it's very dangerous to live next to one if you will do it? So you like danger, or I mean, the question is, it's my daughter. She had in the class. They asked them if the people should live next to the ring of fire. It was a very hard question for her age, but maybe for you it's an easy one.
Would I live in California? Would I live in the Cascades? Would I live in Japan? Yeah, they're really nice places to live, and the volcanoes aren't erupting on a daily basis. So, to answer your question, would I live near a volcano? Yes. I mean, So we went to Goma, right, to the Democratic Republic of Congo, went to Nyiragongo, we interviewed all these people about, like, living near volcanoes, and they were like, the only reason we live here is because the soil is so fertile, and it's amazing, like, the crops are brilliant, and, occasionally the ash comes out of Naimulagira, and it kills the crops, but we live with that, right? We have to live with that, because if we leave here and go somewhere else where the soil's not so fertile, we'll starve and die. So sometimes that question about whether you live near a volcano is taken out of your hands. Now, you're asking, like, a slightly privileged black dude from Acton if he would go and live near a volcano necessarily. I mean, Acton's kind of sketchy at times, but I don't think I'd trade it in. But if somebody said, if I got offered a job in a place where there was a volcano, or in Japan where there's a tsunami hazard, would I go? Yes. I'm not sufficiently scared of the earth that I would allow it to stop me going to an amazing place.
Super. Right.
Thank you.
The gentleman just here, please, Lisa.
Good evening, Chris.
Hi.
I'm Graham Taylor. I'm a second-year student at London Metropolitan University studying sociology. I really enjoyed you tonight. It was a great speech. Thank you very much for what you've done for us tonight, and thank you for your time. I noticed on your actual speech, you was talking about tectonic plates and the way in which the underground actually splits. Is that, and I saw from your speech the way you spoke about lava flows and the dikes and the seals, all to control the lava flow, which spurts up into the air. How on earth did they manage to find out how tectonic plates actually split underneath the ground as a research phenomenon? Because it baffles me how they managed to get underneath the ground to actually work this out.
So a lot of it is not being able to physically get underneath the ground. There's a series of different complementary techniques. So you can go into a part of the earth where there's a mountain range, and from that you can probably deduce that the reason the mountains are there is because two plates have come together and have been uplifted. You could go to somewhere like the East African Rift Valley where the plates are being pulled apart, and there are these giant depressions like the Afar where it's super hot, and you could work out that the Earth's being pulled apart and you can see these giant fractures. So that's superficial observations. Now, those superficial observations have to be linked with geophysical observations. So and geophysics is what we've talked about tonight, is these images which allow us to image down, in these cases, largely for a normal marine acquisition, you could image down to, say, 20, 30 kilometers, maybe a bit more into the Earth's crust. So then you can marry your surface observation with these images I've showed you. And then, in terms of the plates, the other thing you need are kind of these more low-resolution, more regional images, which come from things like seismic refraction and seismic tomography, it's called. And that's where you then get these images like the Mount St. Helens one I showed you, where you're looking at the way these seismic waves are traveling through the whole Earth, which is how we know that there's the core and the inner core, the outer core, exactly, in the mantle, and as we go up. So those layers in the Earth are, and this science didn't happen yesterday or over the weekend. I mean, this has been hundreds. I mean, plate tectonics is a relatively recent phenomenon, right? But it was at the confluence of a number of different techniques, which, when they started thinking about the plates, suddenly a lot of other observations made sense. The rocks were this composition because it used to be in a subduction zone and then got uplifted. And the only way that could happen is because of the plate motions. Does that make sense? So, then it provided that framework for a lot of other geological observations.
Great. We have another question.
Hi. So I'm a metrologist, and again, that rock and roll as well. Question for you with doing the surface of the Earth for observations. You said there's a problem with laying out cables, obviously for whaleys and the like. Have you tried using wireless distributed sensors?
I have not. I mean, I don't do the deployment, so a lot of the data we get are from oil and gas contractor companies who collect the data on behalf of their clients. There are wireless nodes you can place on the seabed, which are the effectively the hydrophones, but instead of trailing them behind a boat, you actually have them permanently installed. And I don't know if they're wireless now, I think about it, but they are a semi-permanent installation on the seabed. The reason being, if you have an active oil field producing, you can keep going back every year, shooting a seismic survey, and actually trying to work out if the oil or gas has migrated through the reservoir, because there's a series of techniques you can use. So you have these semi-permanent arrays on the seabed. Also, it takes out the water column.
Yeah.
So you lose a bunch of energy when you let the air gun go off. The energy travels down, but it has to go through 2, 3, 4 kilometers of water. So if you put your hydrophones down, you reduce the energy coming back doesn't then have to go back through the water column to the hydrophone. It comes back to your sensor on the seabed.
Okay. So the related bit with the idea of distributed sensors is what sort of time resolution do you require? You're talking about distances of 10 kilometers at 7 kilometers per second. So it looks like your epoch measurement's probably a few seconds.
Yeah, and depending on what we call the offset, so the cable length, so the length of the rope behind the boat.
Sure.
So if you have a very short cable length and you're sending energy down here and the cable's this long, if you send that energy down and it returns here, you're not recording it. So if you have a longer cable length, then you can actually image better, more deeply, if that makes sense, because it comes here, it bounces, and then it comes back here, so you need a cable length the length of this table, whereas if you have a cable length just this, you won't get any kind of... So it's what we call, related to what we call offsets.
You're going to have a finite window over which...
Yeah, exactly.
For the spatial system. But for, say, an aerial over the Earth's surface, not on the sea, if you're having distributed sensors, would you have an issue with time resolution and spatial resolution? And how would that feed in terms of the deconvolution?
That's very geophysical.
Yeah. Sorry.
Yeah, that's not my really area of expertise in terms of the acquisition and processing, is what you're talking about, the deconvolution steps. Yeah. There's those challenges, but there's also just challenges of deploying the arrays over a large enough area anyway for all the environmental and logistical reasons you'd have anyway. So, yeah.
Very interesting. Thank you very much.
Thank you.
Chris, I want to thank you this evening. I think volcanoes are truly, truly fascinating. They are awe-inspiring, as you have eloquently shared with us this evening. So, ladies and gentlemen, if you would join me in thanking Chris in the most usual way. Thank you.